What if you could film the fastest thing in the universe? I'm not talking about a speeding bullet, or even a flash of lightning. I'm talking about the frantic, impossibly quick dance of an electron. These are called Attosecond Light Pulses, and they have given humanity a new set of eyes. Eyes that can finally see the frantic ballet of electrons. For their revolutionary work, the 2023 Nobel Prize in Physics was awarded to Ferenc, krausz and Elie Wiesel. What they did isn't just a tech upgrade. It's like we've discovered a new sense to perceive the universe, and what we're starting to see with it is changing everything. For all of human history, seeing that was pure science fiction. The fundamental movements that create our reality, the very basis of all chemistry, biology, and electronics were a complete mystery, a blur that no instrument could ever hope to see, until now, in a breakthrough that is rewriting our understanding of the quantum world. 3 scientists have won the Nobel Prize for creating pulses of light so unbelievably short they last for a billionth of a second. The analogy, grounding an impossible scale to really get your head around this. Let's start with something we all know. If you want a sharp photo of something moving, you need a fast shutter speed. To freeze a running kid in place, 1/1000th of a second is pretty good. To capture the wings of a hummingbird beating 80 times a second, you need to be way faster. And to see a bullet rip through an apple, you need a crazy specialized camera with a shutter that opens and closes in a millionth of a second, a microsecond. Even though they could see the atoms moving, they couldn't see why they moved. The reason is the electron. Electrons are the real architects of our world. They needed an attosecond is 1,000 times shorter than a femtosecond. It's a billionth of a second. That number is so huge, it's hard to wrap your head around. So let's try another analogy. An attosecond is to 1 second what 1 second is to the entire age of the universe. Just think about that. Every single second that has ticked by since the Big Bang. All 13.8 billion years of them, all squeezed into a single second. An attosecond is just one of those cosmic seconds. That's the shutter speed you need to finally capture the dance of an electron. They form chemical bonds, they carry electricity, they absorb and emit light, and they move on a timescale that makes a femtosecond look like an eternity. To an electra, a femtosecond flash is like leaving the camera shutter open for years. All you get is a meaningless blur. Now, let's leave our world and shrink down to the world of atoms. For a long time, scientists dreamed of watching chemical reactions as they happened, seeing atoms actually break bonds and form new ones. This stuff happens on a femtosecond time. A femtosecond is to 1 second what 1 second is to 32 million years. It's a timescale so short it's almost impossible to imagine. Back in the 90s, scientists figured out how to make femtosecond laser flashes, and they won a Nobel Prize for it. They had finally built a camera fast enough to film atoms in motion. It was a revolution. But there was a ghost in the machine. To see the electron, scientists needed a new unit of time. The why. The problem of the quantum blur. So, why go to all this trouble? Why build a camera that can peek into a billionth of a second? The answer is huge. Because what electrons do underpins literally everything. And for decades, this was one of the biggest blind spots in all of science. Take chemistry. Every single chemical reaction, from iron rusting to the cells in your body working, is really just about electrons deciding to leave one atom and join another. Scientists had incredible theories, like quantum mechanics, that could predict the outcome. They had the script for the play. They knew who was on stage at the beginning and who was there at the end. Photosynthesis, the process that powers almost all life, is just an electron getting kicked into action by a photon from the sun, starting a chain reaction of energy. How our bodies make energy is all about a complex electron transport chain. It was a fundamental hole in our knowledge, a quantum realm that was simply happening too fast for us to ever see. To break through that wall, we needed a new kind of light. But again, the real action, the instant an electron makes its move, was invisible. To truly get a handle on these vital processes, and maybe even diagnose diseases at the molecular level, we had to follow the electron. But the entire performance, the most important part of the story, where everything actually happens, was playing out in total darkness. They couldn't see how the actors moved. This wasn't just frustrating for scientists. It meant we couldn't truly control the machinery of chemical change. Then you have electronics. Every computer, every smartphone, every single data center on the planet runs on controlling how electrons move through semiconductors. The speed of our technology is limited by how fast we can flick that electron switch on and off. We've gotten amazingly good at it, but we were hitting a wall. To make a real jump to the next generation of computing two devices thousands of times faster, we had to understand how electrons behave at the exact moment a process kicks off. How do they first react to light in a solar cell? How do they first start moving in a transistor? Without seeing that initial quantum event, we were basically just guessing. And finally, there's biology. Life itself is a story written by electrons. This was the Great Wall. We were surrounded by the results of electron motion, but the motion itself was a blur. The breakthrough, the heroes, and their solution, science usually moves in tiny, slow steps, but every once in a while, she was running an experiment that a train of pulses is amazing. But for a lot of experiments, you need a single, isolated flash to get a clean picture. Krausz and his team figured out a clever way to pull just one pulse out of that train. They successfully created a single burst of light that lasted only 650 attosecans. This was it. This was the camera flash capable of freezing the motion of an electron. They immediately put it to work, tracking the process of an electron being ripped away from an atom, and watching its behavior in real time for the first time in history seemed pretty. They had imagined, built, and proven a tool that could see what was once unseeable. The Great Wall had crumbled. Humanity could now watch electrons move. Simple on the surface, she was firing a powerful infrared laser through a noble gas, like argon. Based on the physics at the time, nothing much should have happened. But what she saw was totally unexpected. As the intense laser light passed through the gas, a whole bunch of new light frequencies popped out the other side. These weren't random. They were overtones, or high harmonics, of the original laser light kind, of like how a single guitar string produces a main note and a series of higher-pitched overtones. It takes a giant leap. The invention of the attosecond camera was one of those leaps, and it was made possible over decades by three key pioneers. Pierre Augustin. There's a basic rule in physics that to create a really short pulse of light, you have to combine a huge range of different frequencies. Julius' discovery was the first sign that you could actually generate the massive bandwidth needed for pulses. She had found the raw ingredients, and, for working independently, figured out how to turn those raw ingredients into something real. One group, led by Pierre Augustin in France, found a way to take the harmonics Julius had discovered and make them interfere with each other in a very specific, controlled way. The result was incredible. They produced and measured a train of light pulses, each one lasting just 250 atoms. It was like they had created a quantum strobe light flashing billions of times a second. The door to the attosecond world had been kicked wide open. The story really starts back in 1987 with analog. The key thing was that these overtones went deep into the extreme, ultraviolet part of the spectrum. This discovery was the seed of everything. The next crucial step didn't happen until 2001. Two different research groups. At the exact same time, a group led by Ferenc in Austria took the final, critical step. Together, Julius' foundational discovery, Augustini's pulse train, and Krauss's single isolated pulse, were a complete revolution. How it works. The magic of high harmonic generation. So how on earth do you make a flash of light that lasts for a quintillionth of a second? The method sounds like pure science fiction, but it all comes down to a beautiful, violent dance between light and matter. The technique is called high harmonic generation, or H. It starts with a ridiculously powerful laser. Not your laser pointer, but a specialized beast that spits out ultra-short pulses of intense infrared light. These atoms are noble because they're restable and do want like to give up their electrons. They hold on tight. But the laser is about to force the issue. These pulses are actually the slow part, lasting a few The electric field of the laser is so insanely strong that it overpowers the atom's own field holding its electrons. The laser field actually bends the atomic landscape, creating a ramp that an outer electron can tunnel through and escape the atom. The electron is free, but it's now caught in the oscillating wave of the laser's electric field. Step 1. The target. This intense laser pulse is blasted into a jet of noble gas, like argon or neon. As the laser's field continues its wave-like cycle, it first yanks the freed electron away from its home atom. The final piece of the puzzle, pioneered by Augustin and Krausz, is how you put them all together. By perfectly controlling the initial laser and the gas, they made sure all these different high-frequency waves were created perfectly in sync. Think of it like a giant orchestra. If every musician plays their note randomly, all you get is noise. But if the conductor gets every single player to hit their note at the exact same instant, you get one single, incredibly loud and stunningly short sound. That's what's happening here. All the different harmonics add up perfectly at one single moment, creating a burst of light with immense power, and a breathtakingly short duration. A single, isolated attosecond pulse. It's the orchestration of light itself to create the fastest camera flash ever made. Then, as the field flips direction, it grabs the electron and violently slams it right back toward the atom it just came from. Because there's so much energy, the light that comes out isn't infrared. It's in the extreme ultraviolet or even soft X-ray range. This entire sequence slingshot flash happens in less than a single This recollision is the secret source. The electron, having soaked up a ton of energy from the laser on its short trip, is now packing a massive kinetic punch. Step 2. The rip. Step 3. Step 4. The flash. When that super-energized electron smashes back into its parent ion, it releases all that extra energy in a single, brilliant burst of light. It happens over and over, on every single half-cycle of the laser's wave. Each collision makes a flash, generating a huge number of high-frequency light waves to harmonics. An Eloelia first discovered, you get light at 3 times the original laser frequency, 5 times, 7 times, and on, up to hundreds of times the original. Step 5. The symphony of light. And this doesn't just happen once. Step 6. The grand finale. So now you have this huge collection of different light frequencies. If you're fascinated by this journey into the quantum world, and if you enjoy these kinds of deep dives, go ahead and subscribe. It really helps us continue to explore the edges of what we know and bring these amazing stories to you. We've got a lot more to uncover. The so what? Real-world applications, okay? So, creating the world's fastest camera is an amazing scientific achievement, but what does it actually mean for us? The answer is that Attosecond Science is getting ready to shake up countless fields, transforming from a pure research tool into a technology that could change our lives. In this futuristic tech, information would be controlled not by pushing electrons around, but by the oscillating electric field of light itself. This could lead to processors that operate at petahertz frequencies, making them up to 100,000 times faster than the phone or computer you're using right now. Attosecond pulses let scientists literally watch chemical bonds break and form in real time. This isn't just for curiosity's sake. If you can understand exactly how a catalyst works at the electron level, you could design new, hyper-efficient ones for industry, saving energy and cutting down on pollution. We can watch how electrons zip through new materials like graphene, giving us the insights needed to finally use their weird and wonderful properties. It even lets us see the very first steps of radiation damage, which is critical for building things that can survive in space or in a nuclear reactor. Using attosecond X-ray pulses, it might be possible to create movies of proteins and DNA as they do their jobs. We could watch a protein fold, or see exactly how a drug molecule connects with its target. This would be a game changer for discovering new medicines and understanding the root causes of disease. Attosecond pulses are the only tool that lets us see, and maybe one day control, how electrons respond directly to a light field. Let's start with electronics. For years, the dream has been to move beyond our current electronics to something called light-wave electronics. Ferenc, one of the laureates, is now focusing a lot of his work here. One of the most promising ideas is for early cancer detection. The thinking is that diseases like cancer create tiny, but specific, changes in the molecules floating in our blood. These changes are too small for normal tests to see in the early stages, but they might be detectable with attosecond pulses. The idea is to take a tiny blood sample, hit it with these ultrafast flashes, and analyze the light that comes back. The molecular vibrations create a unique fingerprint that reveals exactly what's in the blood. The hope is that this could become a simple, sensitive screening tool to find cancers when they are easiest to treat. In chemistry, the applications are just as big, but maybe the most exciting applications are showing up in medicine. And it goes beyond just diagnostics. This technology could change how we understand life itself. The future, from watching to controlling the invention of the attosecond pulse, has thrown open a new window into the quantum world. For the first time, we aren't blind to the fastest, most fundamental processes that build our reality. We've gone from seeing a permanent blur to having a front-row seat to the electrons dance. But the real future here is bigger than just watching. The next, even more thrilling chapter, is moving from observing to controlling. If you can use one attosecond pulse to kick off a process and another one to watch what happens, you can start to figure out how to step in. The ultimate dream is to use these pulses of light as quantum tools like the world's finest pair of tweezers. Imagine being able to use a carefully designed sequence of light pulses to steer electrons down a specific path in a molecule, choosing to break one chemical bond while leaving all the others perfectly intact. That would be the holy grail of chemistry. Controlling reactions with absolute precision. Imagine using light fields to push electrons through a material to create any electronic or magnetic state you want, on demand. This is the future that Attosecond Science is making possible. The work of Pierre Augustin, Ferenc, and Enal Huillier didn't just win them a Nobel Prize. They kicked off a whole new era of science. We're still in the very early days, like someone in the 1600s looking through a microscope for the first time. We are just starting to glimpse the beauty and complexity of a world that has always been invisible to us. What we'll discover next, and what we'll learn to build with these incredible tools, is still a mystery. But one thing is for sure. The journey into the attosecond world has only just begun. If this peek into the future of physics got you thinking, you should definitely check out our video on the mind-bending world of quantum computing, where controlling the quantum realm is already starting a new technological revolution. Thanks for watching.